Welcome back. So the next thing we're going to talk about is the Krebs cycle. So before we really get into it, let's go and talk about where it fits in, what we've done, where we're going, things like that. So we did the big picture. So in our big picture, first thing we did is we started out with a molecule of glucose. We took that glucose to pyruvate. And that's what we did in the last video. That was our process called glycolysis. Glyco, sugar, lysis, splitting it. That was where we started processing our carbohydrates with the end goal of getting energy in mind. So ATP is our goal. So we left off there with pyruvate. But as you might or might not remember from the big picture, we had some more stuff to do between that pyruvate or to that with that pyruvate to get to ATP. So we were out also in the cytoplasm doing glycolysis. So the next thing we have to do is a little process called the pyruvate dehydrogenase complex. And what that's going to do is a couple of things. That's going to convert our pyruvate to acetyl-CoA, the molecule that starts the Krebs cycle. It's also going to get us into the mitochondria. So we're going to cross from the cytoplasm to the mitochondria as part of the pyruvate dehydrogenase complex. So most of our energy making processes are done in the mitochondria. And we'll come back and we'll visit that idea a little bit more when we have more stuff to talk about in the mitochondria. So our goal is, our purpose of the pyruvate dehydrogenase complex is to get pyruvate, get our carbs in the form of pyruvate into the mitochondria and into the Krebs cycle. And that's what we'll spend the majority of our time on in this video today, on the Krebs cycle. What the Krebs cycle does is it makes you the stuff that makes ATP. And I'm saying that very casually on purpose because I think it sticks in your head better more casually. What it's going to do is make things like NADH, FADH2, as in ATP equivalents, as in electron carriers loaded up with electrons, as in it's going to write you checks for ATP. And that's what we're going to make as the product of the Krebs cycle. Then we'll take those checks for ATP, send them to the electron transport chain, that's kind of like the bank, and cash them and get our ATP. So there'll be a few things we're going to talk about with the Krebs cycle that are kind of big deals to keep in mind. We're going to enter the Krebs cycle through the carbohydrate route. So you kind of get carbs on the brain. But the Krebs cycle processes not just carbs, but also fats and also proteins. And we'll come back and we'll talk about those, but I just want to remind you of those now because you might get asked, what's the Krebs cycle process? A, carbs, B, fats, C, proteins, D, all of the above. It's an all of the above, but it's easy to forget the proteins and the fats because we haven't done them yet. So that's something I'll keep reminding you of here and there. So anyway, we'll come back to a couple other things. We'll focus a lot on we're not actually making ATP, we're making the stuff that makes ATP. We'll also talk about this cycle thing. What's a cycle? I'm coming back to where I started. What's the point? So we'll come back and talk about all that. So let's introduce it a little bit first, or a little bit more, I guess. So there's multiple names for the Krebs cycle. And like we did in Biochem 1, I'm not going to give you synonyms unless I think there's equal-ish probability of you seeing them. You've got enough to remember and memorize. You don't need extra. So the Krebs cycle is also known as the tricarboxylic acid cycle, is also known as the citric acid cycle. I always say Krebs, it's more habitual than anything. You're as likely to see citric acid cycle or tricarboxylic acid cycle as you are to see the Krebs cycle. We have the overall reaction here again, and don't memorize it, but I have it here only to remind you, if you get one of those questions, all of the following are products except, all of the following are reactants except of the Krebs cycle, and you come down to two answers. Did you forget I need FAD to make FADH2? Did you forget I need NAD to make NADH? GDP to make GTP? Things like that. Also, I'm not going to go in full slideshow mode here because I need to be able to switch back and forth. It's quicker to stay not in slideshow mode to be able to do that. Okay, so the first thing we're going to do is we're going to do the pyruvate dehydrogenase complex. This is our link between glycolysis and the Krebs cycle. This is our way of getting carbohydrates into the Krebs cycle. And we'll go through the steps. We're going to do this one more so in words, although the structures are in the PowerPoint. So this is our ticket into the mitochondria. That's really important. So we got to pyruvate in glycolysis. Pyruvate looked around and said, oh, I have enough oxygen to continue. Let me go into the pyruvate dehydrogenase complex. Let me go into the mitochondria. Let me go and get ATP for this cell. So the pyruvate dehydrogenase complex is not technically part of the Krebs cycle. I put it in this section because every biochem book puts it in the Krebs cycle chapter. It's a multi-enzyme complex. When you see complex, you're going to think multiple enzymes. Multiple enzymes means multiple steps. So we'll go through, we'll draw it. Irreversible step. This is a one-way street. I can't directly take pyruvate or take acetyl-CoA back to pyruvate. And we'll come back and talk about this more. It gets kind of interesting because it's the reason we can't, we can turn carbohydrates to fat. We're going to do that. We can't turn fats back to carbs. So we can't make glucose directly from acetyl-CoA, things like that. So that gets very relevant in your physiology. It'll get relevant in your nutrition class. And when Dr. Krabbe's saying, well, you can't get there from here kind of thing, this is the why he'll be saying some of those things. So multiple enzymes, pyruvate dehydrogenase is the only one you need to worry about remembering, the name of the overall complex. And we're going to go through the steps, but they're spelled out here also. Okay, so let's just draw it. And again, I'm walking you through the drawings that will become your project when you pull that together at the end of the term. So let's get a new slide. So we're going to walk and talk our way through this. So what we're going to talk about is the pyruvate dehydrogenase complex. The purpose of this one, and I'm not going to take up space writing it because you can pause and rewind me, and I want the space to actually draw it. So my purpose here is I want to get my carbohydrates into the mitochondria. I want to get them into the Krebs cycle so I can continue to get more energy out of them. So for your project, for your diagram, I would absolutely have that on here. So what we're going to do is we're going to take molecule of pyruvate that we made, and of course don't forget we made two. We split that 6-carbon molecule of glucose into 2 pyruvates. So we split the 6-carbon molecule. Before I even ask you, you already know pyruvate has 3 carbons in it. And we're going to convert that pyruvate to a molecule of acetyl-CoA. So we're going to go through the steps. So the first thing we're going to do to that pyruvate is we're going to decarboxylate it. So when we decarboxylate, just like the word sounds, we're going to take a carbon off. When we take a carbon off, we take it off in the form of a carbon dioxide. So here's the thing with carbon dioxide. We kind of don't care about it, but we kind of do. And what I mean by that is it's a waste product. It's on that list of molecules that within the scope of this class, we're going to say, well, we made it, we left it. Another physiology class will talk about what we do with it, how we get rid of it. So for us, we left it there. But we pay attention to it in the sense of if I make one, I took a carbon off of something. If I used one, I put a carbon onto something. One of the most common ways to see if you have any clue about structure, keeping in mind, we're not going to give you a structure, say name it, or give you a name and say draw it like organic chemistry did, but you can't totally ignore it. And a way to see if you're totally ignoring it is say how many carbons are in whatever molecule. So if you get asked how many carbons are in a molecule and you don't know, think about where did I get that molecule? How did I get that molecule? Do I know how many carbons are in it? If you do, the answer will be between that molecule and how did you get there. If you don't know on that one, go back one more step. Where did I get that one? So for example, this is the only carbon we're going to take off of pyruvate. So you already know, as soon as I tell you that there's 2 carbons in acetyl-CoA. Because I have a 3-carbon pyruvate. I just took a carbon off, leaves me 2. So pay attention to your carbon dioxides, even though they're not super important in terms of what we're doing. So we need another molecule to do this carboxylate or decarboxylation. The molecule we need is thiamine pyrophosphate. So we need thiamine pyrophosphate to decarboxylate. This is such a super common question. This is the reason, one of the reasons, or this idea is the reason you made that vitamin chart last term. I know you think you did it because it was 20 points and whatever. That was just your blackmail or your bribery to do it. The whole purpose of it is board notes by you, for you, in your words. Because the thiamine pyrophosphate question can be asked in a number of different ways. So, and of course we can do, your B vitamin questions can always be the name or B1, B2, B3 kind of thing too. So you have to know that, but that's actually not what I'm talking about. I could ask you, well, anybody could ask you, it's not just me. I could ask you very generally, what B vitamin do you need to decarboxylate? You're going to pick thiamine. So there's one way you can get asked the question. What B vitamin do you need to convert pyruvate to acetyl-CoA? Thiamine. What B vitamin do I need for the pyruvate dehydrogenase complex? Thiamine. So really the same question for the most part, 3 different ways, but you've got to be able to pick up on those 3 different ways. So what your best move right now is go back to your vitamin chart, write whatever you need to on your vitamin chart. This is all about you, that when you study it, you would pick up on that question all those different ways. And there's going to be a few places where we're going to do that. Might be asked this way, might be asked this way, kind of thing. And like we've said before, and I'm going to keep saying, half the battle is knowing your stuff. And you guys are going to be fine at that. The other half is picking up on, what are you asking me here? That kind of can be the hard part. So go back to your vitamin chart, edit it, and make sure you'll pick up on that question all those different ways. I'm also going to throw it in the question part. When you get to the question part, I'm going to keep adding it to it as I think of stuff, but you're going to find some repetitiveness totally on purpose. Just little tweaks and changes on the question just to get you in the mode, in the zone, whatever, of being able to pick up on it and answer it. All right, so I took the pyruvate, I decarboxylated it, and I've got this 2-carbon now intermediate. So I want to do my next step. So what I want to do is I want to oxidize my 2-carbon intermediate. What I need to do to oxidize it is I need to attach it to a molecule of lipoic acid. So I need to put lipoic acid into the mix because I'm going to attach my 2-carbon intermediate to that. Then I'm going to oxidize it. So when I oxidize something, I've got to reduce something. When you hear us say or talk about, read about, whatever, we oxidize something, you're always, always, always going to ask that what's in it for me question. What did I reduce? What electron carrier did I just load up with electrons that I can go and do something with that energy? So I will tell you, you reduced FAD to FADH2. But you didn't leave that FADH2 alone. You oxidized it back to FAD while you reduced NAD to NADH. So NADH is the product I actually made. Then I still have that 2-carbon intermediate now that I've oxidized. I'm going to stick a coenzyme A on there, and I've got my acetyl-CoA that I can go and put into the Krebs cycle and do my Krebs cycle. All right, so let's talk about questions. If we were in class, somebody's hand would come up right now. What kind of questions are we going to get asked? And and everybody looks. Here's the thing that happens with that. Somebody sticks their hand up. What kind of questions are we going to get asked? And everybody looks at them like, I can't believe you're asking that. That's such a great question to be asking. If you're that person, keep doing it. Tell them all, get over it. Tell them all to thank you for it. And here's why, because asking that question, whether you're doing it out loud or to yourself, you should always be doing that. That hones in your studying. Like here, what kind of questions would I get asked on that? The questions, what you're going to notice from here through the rest of the class is our questions are either very purpose driven. So they might be, why am I doing this? Well, I ate carbs, I have enough oxygen, and I need to get those carbohydrates into the mitochondria, into the Krebs cycle, so I can get the energy out of them. So there's your purpose driven part. Or a really common way to get asked questions, kind of the other direction, is the nitty gritty detail stuff. Common way to get asked that is all of the following are products except, or all of the following are reactants except. So let's talk about that. We're going to talk about a way to remember that. And we're going to talk about mnemonics. I have no idea in this world why, but traditionally, when you're teaching a class, you don't give mnemonics. And I never understood why. You have to go and get them on the black market, whatever, later, and I don't get it. So anyway, if I have a mnemonic that's, I guess, no worse than PG rated, I'll give it to you. And half the reason is I don't see why not. The other half is most of these mnemonics that have been around since time began have some kind of hole in them, a place where if you're relying solely on the mnemonic, you can mess up. Well, whoever's writing your questions probably learned the same stuff using the same mnemonic and probably messed up in the place that it's really easy to mess up on it. So I want to be able to talk to you about where you can mess up so you don't. So that's the other reason we're going to do them. So you probably want your diagram that you just drew in front of you while we're doing this. I want space to draw so you can see it, so I'm going to do it on a separate slide. You might want to, you might not want to. All right, so the mnemonic is these 5 coenzymes love nutrition. And like most mnemonics, what we're using is the first letter. I guess we could use the co on coenzymes. Traditionally, the mnemonic is used for what's going in. We're going to use it for what's going out. So in reactants, out, of course, is our products. Sorry, these are really crooked lines. I'm drawing kind of vertically on another monitor. Okay, so let's go through our story. We took that pyruvate. First thing we did is we decarboxylated it. So if I'm decarboxylating, I made a carbon dioxide. It's a product. To be able to do that decarboxylation reaction, I needed my thiamine pyrophosphate. I'm going to abbreviate it. So that was my first step. Now I've got that 2-carbon, I have that 2-carbon intermediate. I take that 2-carbon intermediate and I attach it, I bind it to a molecule of lipoic acid. So I need a lipoic acid. Once I have it attached to a molecule of lipoic acid, I can oxidize it. When I oxidize something, I've got to reduce something. I'm going to reduce FAD to FADH2. But I'm not going to write the FADH2 down yet because it's not a product. I don't leave it alone. I take it and I immediately oxidize it back to FAD. So I come back to FAD because I reduce then an NAD to an NADH. You might want to, maybe put your little FADH2 in parentheses in the middle that it's neither. Whatever you need to do to keep from getting mixed up on, I make it, but I immediately use it. So my NADH is truly a product. I get that. I make it, I can use it, I can go and make ATP out of it. Then I take that coenzyme A, back to your vitamin chart, put that onto the 2-carbon intermediate, and I get my acetyl-CoA. So, what color do we want? I love having colors. Here's my reactants. Here's my products. But here's the hole in the mnemonic. That's not all my reactants or all my products. So if you just learn your little mnemonic, memorize it, and don't have an understanding, here's where you get in trouble. Think about what reactant, that's kind of a big deal in this, that we're totally ignoring here. We need a thicker line for this, right? What product? And if you only knew the mnemonic, you'd totally miss those. So whoever's writing your questions probably did totally miss those and mess up when they were a student. So it's really easy to set up a question to do that. So here's the other thing with mnemonics. They're not engraved in stone anywhere. Change it. These 5 coenzymes love a pretty nutrient. So pretty, whatever. Make something up. But whatever you do, make sure you don't forget, kind of the major product and reactant in this. Okay, so that's our pyruvate dehydrogenase complex. So at this point, we've taken that pyruvate, We've crossed into the mitochondria. We've made an acetyl-CoA out of it. We're ready to do the Krebs cycle. Okay, so, oh, I'm sorry, I forgot regulation. Pretty straightforward. If I have energy, I don't need to do the Krebs cycle, so I don't need to do the pyruvate dehydrogenase complex. There's my high ATP inhibiting. If I already have acetyl-CoA and NADH, I know I can get energy. I have the products of the pyruvate dehydrogenase complex. I'm good to go. If I have AMP, I don't have ATP, I better get going and do it so I can do the Krebs cycle. So don't start memorizing every little thing with regulation. Reason your way through it. You'll make life an awful lot easier for yourself by doing that. Okay, 8 steps, 8 enzymes. Don't worry about that. Let's just do it. Okay, let's go to the diagram first and talk about a couple of things. I'm not skipping anything. It's just easier to talk about it on the picture. So I'm going to put another slide in and just keep, I'm going to use multiple copies of the diagram, and we'll talk about that in a minute. I'm going to use multiple copies just to stay cleaner. I assume you want to cut down volume. That's not an assumption. That's something I know. So to do that, I assume you're probably going to put everything on one diagram. I want you to be able to see what we're talking about, so I'm going to do multiple. Okay, so what we're going to do is we're going to start with this molecule of acetyl-CoA, and that's going to come into the Krebs cycle. So let's back up for a second with this diagram. Last diagram that we used was the glycolysis diagram, and I gave you one in words. Some students want the words because you're going to get tested in words. You won't get, here's the reactant, which product does it make? Here's 4 structures, pick it. You'll get, here's the reactant, which product does it make? Here's the name of the 4, pick it. You know, glucose 6-phosphate, fructose 6-phosphate, whatever. So for that reason, some students like the words. Here's one in pictures, in the structures, pictures. I like that. I'd rather see pictures than read words. I guess that says something about me. So I like to see the structure in my diagram. So we're going to do one that way so you can try that. Then you're going to say, I like this way, that way, whatever, and pick it. So again, with the diagram, you're welcome to use mine. It's in the resources on Brightspace. You're welcome to totally ignore it, draw your own, find your own. There's a million of them on Google Images or wherever else you choose to get your diagrams. So anyway, that's the story here. So it's a cycle. Well, if it's a cycle, there's a molecule that's both a product and a reactant. And there is a molecule that's both a product and a reactant, oxaloacetate. So there's a question right there. Which of the following molecules is both a product and a reactant of the Krebs cycle? So if it's a product and a reactant, I start out with it and I end up with it. So what's the point? Why do I want to do stuff, do processes that are cycles? Well, let's talk about that. So what I have coming in is I have that acetyl-CoA coming in. Right now, that acetyl-CoA contains a whole bunch of energy. It contains the energy, most of the energy that the pyruvate had, that's a little less than half of the energy the glucose had, and so on. So I've got lots of energy contained in that acetyl-CoA. Then I've got that oxaloacetate. I'm going to abbreviate it. I'm going to say no energy very little energy, but it's kind of my facilitator, my molecule that I need to make this process happen. So what's going to happen is the oxaloacetate is going to react with the acetyl-CoA and make something. It's going to make citrate actually, but we'll get into all that. Then the citrate's going to make something else, something else, something else. And we'll go through the something else's and get our, at the end, oxaloacetate back. So when you first look at that, it's like, all right, well, whatever. So I went through and I made this and I made this and I had to learn an enzyme and look at all these structures. And I ended up back with what I started with anyway. So what's the point? Well, we're going to talk about what's the point. Here's what the point is. As I go through and I make the intermediates and make these molecules along the way, I'm also going to make other stuff like NADH. In fact, it's not just one NADH. We're also going to get bleed off an FADH2, a GTP. So what we're doing is we're starting with this molecule that contains lots of energy. And as we go through, we're taking a little bit off. So we'll have something in between that contains a little bit less. Take a little bit more off, something in between that has a little bit less, little more off, little more off, little more off, till we finally get down back to our oxaloacetate, the molecule that really doesn't have much energy. But here's the thing that happens. Because of the whole academic thing, you've got to know what, and so on in the Krebs cycle. And you know they're going to be test questions and the usual. So you tend to focus there. And I get it because you've got to get through the class and everything. But the important part is really what we get as a by the way. And the reactions will even be written kind of by the way. We'll have, isocitrate makes alpha ketoglutarate, and this little by the way, NAD makes NADH. And the way it's written, sometimes this will even be in a smaller font. The way it's written, to me at least, kind of minimizes the importance of it, when the important part that we really get something from is all of these molecules that come out of it on our way from oxaloacetate back to oxaloacetate. So that's a big thing you need to recognize with the Krebs cycle. And it's a really, really important thing, because otherwise you end up sitting there thinking, all right, well, I started out with oxaloacetate. I already had it. And I went through all these steps, all this stuff, all this whatever to get it back. Why did I bother? You bothered because you got all these molecules that will go and give you ATP. So it's the stuff that's written as kind of by the way that's really the important part of the Krebs cycle. So even on our diagram, the stuff that's written, oh, by the way, here's a little NADH. By the way, here's a little NADH. That's the important part. So the fact that you started with an oxaloacetate, went back to having an oxaloacetate, kind of doesn't matter in the whole thing. Okay, I'm going to recycle this diagram, just erase some stuff on it, since I didn't write too much on it. And we will hit the Krebs cycle. So my first reaction, I'm going to start out with that acetyl-CoA, and this is my committing step. I'm going to condense it with oxaloacetate, and I'm going to hydrolyze it. So condense them, put them together, hydrolyze it. hydrolyze it, put a CoA, or take the CoA off, put the water in, the H and the OH, the hydrogen and the hydroxyl, and I'm going to end up with citrate. This is my first irreversible step. Well, it's my first step, but it happens to be irreversible, and this is my committing step. So I'm going to take that oxaloacetate, here's my oxaloacetate, I'm going to condense it with my acetyl-CoA, hydrolyze it, and get a molecule of citrate. I wouldn't be drawing these squares on your diagram. I'm just doing it so you can see where we are. The enzyme that catalyzes this is citrate synthase. It's regulatory, and it's our committing step. And we'll come back and talk about what regulates everything. So it's an enzyme that you need to know. Okay, so then I've got the citrate. I'm going to rearrange it into isocitrate, kind of. So I am going to make an isomer. I have my citrate. I'm going to make isocitrate out of it, but I'm not going to do it in the usual way of just rearranging something. What I'm going to do is I'm going to dehydrate it, take my hydrogen and my hydroxyl off, flip them over, and put them back on. But I'm putting them back on different carbons. So I'm going to dehydrate. There's my H and my OH. Take off my hydrogen and my hydroxyl. So I took them off. Then I'm going to put the hydroxyl on the carbon the hydrogen came off of, the hydrogen on the carbon the hydroxyl came off of. So I am doing water out and water in, but it's a wash. Water out, water in. It's one in, one out. So I break even. I am getting the isomer, but I'm not just rearranging stuff. So my enzyme's an aconitase, not a mutase, not an isomerase, because of the way I'm making that isomer. This is a reversible reaction, so really not much of anything to write on the diagram. So we won't go to it yet. Okay, so then I've got that isocitrate. I'm going to do a couple things to it. I'm going to oxidize it. Okay, so here we go. As soon as I say I'm going to oxidize something, you're going to say, so what's in it for me? What did I reduce? And I will tell you. You reduced NAD to NADH. Here's the first little bit of energy getting bled off of this system. I got that NADH. So it's an irreversible step. It's a regulatory step. So I got my NADH. Then I'm going to decarboxylate also. So I have the intermediate. We're not going to worry about the intermediate. And again, I choose whether we're going to worry about it or not based on a majority rules decision on which book worried about it, which one didn't, with the books that the boards use, and no one really pays much attention to it. So I won't take up any of your brain cells with it. But just know there is an intermediate in there because I do these two things. I oxidize while I reduce NAD to NADH. Then I decarboxylate. I take a carbon dioxide off. Again, carbon dioxide is not super important, other than tells me how many carbons. So let's look at a couple things in our diagram. Okay, so this was, let's put our arrows in here too. The one downside of this diagram, as much as I like it, it has the arrows just go in one direction because it's going through the conversation of this molecule makes this molecule makes this molecule. So we were at citrate, had citrate, then we did that dehydration hydration, which is actually reversible, and got to our isocitrate. So if you're following me through here, I probably wouldn't be putting squares around everything. I'm just doing it so you know where we are. I would be doing the arrows. All right, so we've got our isocitrate. Have our isocitrate. I'm going to do two things. irreversible reaction, so we'll put the arrow in so I don't forget. We're going to oxidize it. That means we're reducing something. We reduced NAD to NADH. Got one NADH. I won't write that because I don't want to take up the space doing it. I also decarboxylated, so I got a carbon dioxide. It's a product of the Krebs cycle. So if it's, all the following are products except, it's truly a product. It's just not one that does anything for us or gives us anything. So we end up with that alpha ketoglutarate. But let's talk about the carbon dioxide for a second. We said we have 2 carbons in an acetyl-CoA. I condense that with a 4-carbon oxaloacetate, meaning I put them together. That gives me a 6-carbon citrate. I rearrange by dehydrating and hydrating my 6-carbon citrate into 6-carbon isocitrate. Now I decarboxylate. I have 6 carbons. I took one off. My alpha ketoglutarate is 5 carbons. So again, it's a waste product. We don't do anything with it, but it does help you on the how many carbon thought, questions, whichever. Okay, so we have alpha ketoglutarate. Now, oh, and that was a regulatory enzyme. I'll put that on the next, when we go back to the diagram. Now, we're going to do kind of exactly the same thing again. We're going to oxidize alpha ketoglutarate. So you're going to say, oh, what did I reduce? I will tell you. You reduced NAD to NADH. What did you get? You got an NADH. We're going to decarboxylate. Oh, here's another carbon dioxide coming off. Kind of don't care, except it tells me how many carbons are in the molecule. I'm also going to put a CoA on. So this is my third and my last irreversible step. So let's go to our diagram. So I have my alpha ketoglutarate. I'm going to oxidize it. What do I reduce? I reduce NAD to NADH. So I just got another NADH. Let's back up on that. The enzyme is alpha ketoglutarate dehydrogenase. So remember what we're doing with oxidation and reduction. We're gaining and losing electrons. Oxidation's losing, reduction's gaining, oil rig, and all that stuff. So the electron, though, travels with the proton, makes a hydrogen, makes an H, chase your H's. That's how we figured out what's getting oxidized, what's getting reduced. So since it's all traveling as a hydrogen, how do you like the name dehydrogenase as your enzyme name? Pretty descriptive, right? So use that. Alpha ketoglutarate dehydrogenase. I also had isocitrate dehydrogenase. I forgot to write that that was regulatory. And your alpha ketoglutarate dehydrogenase is regulatory. And again, we'll come back and talk about what regulates them. Again, one-way street, one-way reaction. Like we said, we also decarboxylated. So we got the acetyl-CoA, a 4-carbon molecule. And everything from here on in is going to be 4 carbons. So how many carbons are in whatever molecule in the Krebs cycle? This is pure coincidence. I couldn't have planned this if I tried. But our alpha ketoglutarate that's at 5 o'clock just so happens to be our 5 carbon. So just so happens to be at 5 o'clock in this particular diagram. Everything before that is 6 carbon. Everything after that will be 4 carbon. We're not going to add or take away any carbons between now and the end. So let's go back, though, with enzymes. Let's go back to what you need to be keeping track of. Remember when we did enzymes, we said enzyme names are pretty descriptive, and we did it kind of casually. We said the enzyme name is what the enzyme does or what it does it to with an A's on the end. So probably comes from the Latin. I never bothered looking. But kinases put phosphates on. So if you're putting a phosphate on, it's probably going to be a kinase. Remember our enzymes that make isomers, isomerases, isomer A's. If we're making a little change, little isomer, it's a mutase. Now we're oxidizing and reducing, moving hydrogens with dehydrogenases. Super, super important that you keep track of that and think about that. Don't just memorize them, because you might get a question sometime, which of the following enzymes does whatever reaction? And you might be looking at the reaction like, I have no idea what this reaction is, or I forget, or whatever. But you can start digging through. Well, what's the reaction doing? Do I have a phosphate going on? Let me go looking for a kinase. Is it an oxidation reduction? Let me go looking for a dehydrogenase, an isomer, isomerase. So you can narrow it down from a question that you're looking at thinking, I have no idea, down to, maybe a 50-50, maybe the answer. So use that. Also, anything you can do to systemize you and things like that will help you, because as you're probably starting to see at this point, it's kind of a lot of volume in this class. And I, I'm not that professor that thinks my class is the only one you're taking. Um, so I get a lot of stuff. I know everybody else has a lot of stuff, giving you a whole lot of stuff you have to know. So we will spend time on trying to systemize you and manage the volume. All right, so I've got this 4-carbon succinyl-CoA. I didn't mean to do that, but whatever, it doesn't matter. Okay, so let's go back. Okay, so the next thing we're going to do is a substrate level phosphorylation. Okay, we're going to put a phosphate on something. It turns out we're going to put it on a GDP. We're going to convert our succinyl-CoA to succinate. We're going to take that CoA off. So we have succinyl-CoA. We're going to take that. We're going to take a phosphate. We have energy. So we have a phosphate and we have GDP. So a phosphate plus energy, even though there's kind of nothing to write there for energy, right? Plus energy if you want to and need to in your notes, plus GDP makes GTP. So we're going to do that. We're going to take the CoA off. We're able to do this because we have the energy there to be able to do it. So let's go to our diagram and add it and talk about some stuff. So I've got my succinyl-CoA. Got my succinyl-CoA. I'm going to take the energy from the succinyl-CoA. I'll take the CoA off. Doesn't really matter. I'm going to take the energy off, out, whatever. I'm going to use that energy to put a phosphate and a GDP together, and I'm going to get a GTP, and I'll get my succinate. Reversible reaction. But let's talk about that GTP. Where we're going to go next with the Krebs cycle is, what are we making? We're making all these NADHs, we're making the FADH2, we're making the GTP, we're not making ATP in the Krebs cycle. Zero, none, nada, none. And really, really important that you remember that. So the product of the Krebs cycle is this GTP. Then the GTP will go and make an ATP. But the Krebs cycle didn't make the ATP. The Krebs cycle made the GTP. The GTP made the ATP. And at this point, if I were a student, I'd be thinking, oh, come on, you're splitting hairs here. Yeah, I am. But it's the way questions are set up. If you get asked how many ATP does the Krebs cycle make, go looking for 0. And we'll talk about how somebody writing questions will mess with you on that 0, but you're looking for 0. If The only time you're not going to pick 0 is if it's not offered. If and only if it's not offered, then you'll count that little ATP, but only if it's not offered. And we'll talk about that a little bit more, but it's some strategy on questions because all but one of the board legal books or whatever they are says 0. One counts that. When you get questions, we don't know where your questions are coming from. So we're playing an odds game. So odds are it came from one of the majority of the books, not, the one outlier. So that's why you're going to pick 0. If and only if 0 is not offered, then you'll pick that ATP or pick that one for that ATP. Okay, so I've got my succinate. Let's go back. So far I've gotten 2 NADHs, I've gotten a GTP, and one more thing about that, let's talk about that. Remember, let me just remind you, bring you back to Biochem 1 for a second. Remember what we said about anything TP. For our purposes, they all work the same. I've just got a guanine instead of an adenine on there. But the business end of the molecule is the phosphates, so that's the part that does what I need to do. So they work the same. But since you've got to be counting and accounting for ATPs, you've got to recognize that it's different. So it works the same, does the same thing, but it's not an ATP. So keep that in mind. Also, I've gotten my 2 carbon dioxides. Help me know how many carbons I have, but they're not really doing anything for me. Okay, let's go through, we'll stay on this slide to go through the next, well, I don't know, doesn't matter. Let's go through the next couple steps. So I've got a succinate now, and I'm going to oxidize my succinate. Oh, if I oxidize something, what am I reducing? What's in it for me? What's in it for me is I'm going to reduce FAD to FADH2. So let's go to the diagram, and we're going to talk a little bit more about that reaction. So I've got my succinate, I'm going to oxidize it to fumarate while I reduce FAD to FADH2. So got something else that's going to go and give me ATP. But let's talk about this enzyme. This enzyme needs its very own color. The enzyme, pink wasn't a good choice. We'll do green. Okay, so you have to know your regulatory enzymes. Depending, again, on what book you're reading, some books will call succinate dehydrogenase regulatory. Some will say it's not regulatory. This reaction's reversible. So hang on, how can it regulate? Up until this point, when we've been saying regulatory, we mean the strict allosteric, activate, inhibit, remember the homotropic, heterotropic stuff, definition of regulation. By the strict allosteric definition of regulation, succinate dehydrogenase is not regulatory. However, succinate dehydrogenase is also a component, it's a protein complex in the electron transport chain. The process we're sending all these ATP equivalents to convert them to real ATP. Because it's part of both, it does a couple things. One is it's your literal physical link between Krebs and the electron transport chain. That's a really common question. So which of the following enzymes links the Krebs cycle to the electron transport chain or links the Krebs cycle to the inner mitochondrial membrane? You're going to pick succinate dehydrogenase. And I will absolutely ask you that question. So it does do that. But by being in both, it can have kind of a bottlenecking effect. So it can regulate in that sense, but not in the allosteric sense. So is it regulatory or isn't it? What do we do with it here? So let's talk about a question for a minute. I'm not going to do this to you, but if somebody else does, I want you to be able to handle the question. So let's say you get the question, all of the following enzymes regulate the Krebs cycle except. Common thing. Not going to be perfect on the grammar. It takes too long. So we have citrate synthase on there, regulatory, no one argues. Isocitrate dehydrogenase, regulatory, no one argues. Because remember, it's an accept question. I'm not going to write it all out. You get the point. Alpha ketoglutarate dehydrogenase. Regulatory, no one argues. So these three, they're regulatory. No matter what book you're reading, whatever. No one argues that. So if you get this question this way, and like I said, I'm not going to do this to you. Succinate dehydrogenase. This is what you're going to pick. This question is forcing you into saying it's not regulatory. So based on your options here, you know whoever wrote this question is defining regulatory as the strict allosteric enzyme definition of regulatory. Or you might get it this way. Well, you won't get an E, but I'm going to put an E on just to something else. Another enzyme. And of course, one of these three wouldn't be there because you always get 4 options. If you get it this way, say 2 of these and this, you're going to pick the something else. Because you know then whoever wrote the question is being much broader. Can it do anything to regulate the Krebs cycle? Yes. So then you have to pick whatever else you're given because those are the only things that have any regulatory effect on the Krebs cycle. So sometimes I'll say regulatory effect with the succinate dehydrogenase. So anyway, like I said, I'm not going to do it to you, but I just want you able to handle it in case you do see it. Okay, so we have fumarate now. Very often between 2 oxidations, we're going to hydrate. Because what are we doing when we're oxidizing? We're taking an electron off to put it on something else. Well, it's traveling with the proton, hydrogen, whatever. So if I can open up that double bond, put a hydrogen and a hydroxyl on, I'm setting up for my next oxidation. So that's exactly what I'm going to do. I'm going to take my fumarate, open up the double bond, put a hydrogen and a hydroxyl on, and have my malate ready to oxidize again. Nothing really to write there. We'll go to it in a minute. Then I'm going to oxidize my malate back to oxaloacetate. What did I reduce? I reduced NAD to NADH, got my third NADH, got the last little bit of energy I'm getting out of there, got my oxaloacetate back to do it all over again. So let's go to the diagram. Maybe. Okay, so water has to go in. That's going to get important in a minute. I hydrate, fumarate to malate. Still 4 carbons if you want to have your 4 carbons. Then I reversible. Then I oxidize, reversible, malate to oxaloacetate, and I get that third and final NADH out. Get my oxaloacetate back. I'm ready to do it all over again. Okay, there's the Krebs cycle. So now I probably drew more on here than you did. I made a mess, so I'm going to go to another slide and we'll talk about a couple of things. So you have to know what makes what. You have to know, let me make that bigger, the intermediates of the Krebs cycle. So there just so happens to be a mnemonic for that. There's a few. I'm going to give you the total G-rated one. And again, I'm giving it to you both. I don't see why not, but also because there's a hole in it too. All right, so it's a sentence. So I take the acetyl-CoA and the oxaloacetate, condense them, and I make citrate. So it's going to be the usual first letter of the word thing. So for citrate, can. I'm going to ask a question. Isocitrate, I. Alpha-ketoglutarate, keep. Succinyl-CoA, silly. Succinate, string. Fumarate, for. Malate, my. Oxaloacetate, office. And of course, there's a couple more interesting versions of it. So be careful though, it's the first letter thing, and whoever's writing you a question learned the same thing with possibly the same mnemonic. And we have two S's here. So two S's, the most likely thing to get asked is what's alpha-ketoglutarate make? So alpha-ketoglutarate makes succinyl-CoA. Succinyl-CoA makes succinate. So I had a class about 5 years ago. They added to this. They said succinate is always late. So succinate is always late, meaning it's the later one. So can I keep silly string for my office? We're going to answer that question, and we're going to answer it with the products of the Krebs cycle. So what are my products? NADH, wherever it is, GTP, FADH2, and NADH. I'll answer your question, can I keep silly string from my office? No, no. So pretty emphatic no, and some instructions. Go find nurses. Okay, so if you go and Google that mnemonic, you'll find multiple versions of it. But one of the versions is go find hot nurses. What the hot is the H of the H2O. But here's your problem. NADH is a product coming out. NADH is a product coming out. GTP, product. FADH2, product. NADH, product. H2O, reactant. So you can see where all the following are products except, all the following are reactants except, where you can get messed up on those questions if you don't recognize water is going in. So no hot nurses for you, just plain old regular nurses. And if there's any nurses in the group, I don't mean to offend you. So water is a reactant, not a product. So don't get messed up there. Remember, the water here is a wash. We had water in, water out. We're talking about net changes. So what I would probably do is I would make sure I can write this little sentence, can I keep whatever, and put my, no, just to help me check up on myself and, remember what's going on. And of course, I know if I'm going from, say, isocitrate to alpha-ketoglutarate, and I get an NADH, this has to be an oxidation. Alpha-ketoglutarate to succinyl-CoA, get an NADH, gotta be an oxidation, stuff like that. So you can help yourself back information out of it, if that makes sense. So that's a little mnemonic there. Like I said, there's a million versions, some a little more colorful than that, but colorful will cause me a tremendous amount of paperwork. So we won't do that. All right, let's talk about the regulatory enzymes. You're going to love how easy this is. So we have 3 allosterically regulated enzymes. No one argues. So they are citrate synthase, isocitrate dehydrogenase, alpha-ketoglutarate dehydrogenase. So let's talk about what regulates them. This is so easy, you're going to love it. All 3. Energy. And at this point, you should be saying, well, yeah, that makes sense. Because it's an energy-making process. If I have energy, do I need to do it? Nope. So if I tell you you have ATP, you have NADH, anything indicating you have energy, you're going to say, shut it down, inhibit it. Or if you don't have energy, what are you going to do? Activate it, run it. So easy there. Oh, before I forget, let's look at something. Let's look at NADH and FADH2. And I want to remind you of something. You did this on your vitamin chart, and this is another place I'm going to chase you back to your vitamin chart. Take a look at your vitamin chart and look at what vitamin you need to make NADH. What you're going to find is it's niacin. What vitamin do you need to make FAD? You're going to see it's riboflavin. So I need niacin. I need riboflavin. I'm saying it kind of weird to emphasize the F, but I want to emphasize the F. So if I don't have niacin, I don't have NAD. If I don't have NAD, can't do my Krebs cycle. If I don't have riboflavin, I don't have FAD. If I don't have FAD, can't make FADH2, I can't do my Krebs cycle. So a common thing to get asked is, what B vitamins are needed for the Krebs cycle? Here's where you're going to go looking. You're going to be looking for niacin, or you're going to be looking for riboflavin there. Okay, I probably just did a whole bunch of slides without. Yeah, we did these. Okay, let's talk about something for a second here. If you are an arrow and electron drawer and all that, and I recognize that I'm encouraging you to be, because I think you need to see that and know that and do that. You're going to go through and say, I don't need these 8 steps. I think you can get from acetyl-CoA and oxaloacetate back to oxaloacetate. If you're doing it just purely mechanically, I think you can do it in like 5 steps. Here's the thing though. If you're doing it purely mechanically like an art project, you're ignoring energy. So we don't, and you're going to find that when you ask me a lot, well, why do I do this and this? The answer a lot of the time is going to be energy. That step that you were kind of bypassing when you're just very mechanically drawing it, you didn't have the energy to really do. So that's very often the reason, or it's at least part of the reason, we have more steps than just very mechanically art project-y you would need to get from point A to point B. The other thing, and I'll keep reminding you of this because it's easy to get so focused on this makes this, makes this, makes this, because that's the question you're going to ask me. And you kind of lose a little bit of the rest of it with your blinders. But don't forget, all of these molecules can go leave the process, go and do other stuff, or they can come in from other processes. So what I mean is we kind of did step 1, step 2, step 3, 4, 5, 6, 7, 8. You might not start with acetyl-CoA. You might start at step 3 and something comes in from someplace else and finishes. Or we might take the acetyl-CoA, go to citrate, isocitrate, alpha-ketoglutarate, and leave and go and do something else. So some of these intermediates that you look at, oh, well, what do I need that for? You need it for another process that we haven't talked about yet. So keep that in mind when you're looking at it and thinking, I don't need to do all those steps. We could have done this. You can't, or you didn't, either because of energy or you need that molecule for a particular reason, or it comes from somewhere else for a particular reason. Because don't forget, we just put carbohydrates into the Krebs cycle. We've got to get proteins in somehow, and they'll be one of the things that come in not necessarily at step 1. And we're going to have a fat story. We're going to have some stuff in and out because of fats also. So you're going to see that happening. And let's talk about something else and get it out of the way, because this is usually the point where I see a little bit of frustration. Your The question will come up, why do I need to know the Krebs cycle to be a chiropractor? Well, you are never going to sit down with a patient, at least if you ever want to see them again, and say oxaloacetate and acetyl-CoA condense and make citrate, which makes isocitrate, which makes alpha-ketoglutarate. If you do that, they're going to look at you like you're losing your mind. So you're not going to do that. The other thing is, if I run into you in 5 years or whatever, and if I ever said to you, what are the regulatory enzymes of the Krebs cycle? You're going to look at me like I'm losing my mind. You're not going to remember. And it doesn't matter. You're going to be a perfectly competent, successful chiropractor, even though you don't remember the regulatory enzymes of the Krebs cycle. But two things there. One is you've got to be able to apply this stuff to patient care. The most direct application you're going to see is in your nutrition class that you're going to do in Try 4. Dr. Krabbe builds right on this. Nutrition is nothing more than applied biochemistry. I don't know how excited he is. Well, I do know he's not too excited about me calling it that, but it really is that. So you've got to be able to apply this stuff. Nutrition, no one will argue, directly applies to patient care. Whether you choose to do anything with that nutrition or not, what your patients are eating is going to affect them. So you will apply it, and you can apply it from the big picture. And what I mean by the big picture is, well, the Krebs cycle makes energy. If the Krebs cycle isn't running properly, the patient's cells are not going to have the energy they need to do whatever. And here's why whatever problem they're having could be happening. So you're going to apply it, and it's important that you apply it. You'll see it applied in your physiology classes. It's just not as easy a direct application yet until you get a little more physiology under your belt than you have now. So you're going to apply it, and you need it for that. As far as what molecule makes what molecule and what enzyme does it, you need to do that, at least I believe, once to own the material. You can't apply what you don't own, and you need to go through that process at least once to own it. Of course, that's the stuff boards likes asking you, so for a very pragmatic reason, you need to know it. And I know that's the more immediate reason that's on your mind right now. But you also need to do that to really own it. Some of that, unfortunately, is a little bit of memorization. And if I could ever figure out a way to make it not memorization for you, I will absolutely let you know that. But so far I haven't. So I just want to confront that, be upfront with that. I recognize there's some memorization. I recognize there's some stuff that you're never going to directly apply in your career as a chiropractor, but it is stuff I think you need to go through, learn to own the material so you can apply it. Okay, there's a couple definitions. I wouldn't get too hung up on them, but we said we have molecules coming in from other processes. Those are anaplerotic reactions, replacing an intermediate, anaplerotic, or some of our intermediates can leave in amphibolic reactions. Some examples, we're going to do all these. And that's it for the Krebs cycle. Well, kind of. Let's do one more thing. That's it for the PowerPoint. Let's talk about something. This is the best place to talk about it. I don't know where it really fits in with the book chapters. I'm not following the book very well, and it's a decision I made years and years ago, and I know most of you aren't buying books anyway, but I'd rather put stuff where it logically fits than where somebody else decided it goes in a book. The books weren't written for chiropractors. They were written generally trying to keep everybody happy. All right, so let's go through our processes and what we did. So we started out with a glucose. Let me write over more to the left. I need room to work. We started out with a glucose. We did glycolysis, and we got 2 pyruvates. So this was our glycolysis. We took those 2 pyruvates, we went through the pyruvate dehydrogenase complex, and we made acetyl-CoA. So we did our pyruvate dehydrogenase complex. Then we took that acetyl-CoA, did the Krebs cycle. Actually, I don't want to write it there. Did the Krebs cycle. Then we did electron transport. So let's go back and talk about what we just got in the Krebs cycle, and we'll come back to this diagram. So in that one round of the Krebs cycle, so one round of Krebs, what did I get? I got 3 molecules of NADH, I got 1 molecule of FADH2, I got 1 GTP. I got no ATP. So let's talk about what we're going to get from those. 1 GTP will immediately just go and become an ATP. We saw that. Take the phosphate off of GTP, get GDP back, put it on ADP, we get ATP. 1 FADH2 is the equivalent of 2 ATP. So times 2 ATP per FADH2, that's going to go and give us 2 ATP. 1 NADH is going to be worth 3 ATP. So we're going to have 3 ATP for each NADH. So those 3 NADHs are going to go and give us 9 ATP. Let's go back and revisit these numbers. Anyone who took biochemistry in the last 10 or so years is saying, whoa, hang on here. And NADH is 2.5 ATP and FADH2 is 1.5. You're right, but you're accounting for heat. I'm not. So my big disclaimer here is not accounting for heat. Get used to seeing it. This is kind of like, remember in general chemistry, everything's at constant temperature and pressure, constant temperature and pressure. And at a point you saw it and didn't see it. You just read it and blasted by it. Same idea. The reason I'm sticking with these old numbers, even though more recent editions of books are accounting for heat and doing the 1.5 and 2.5, is there's still board questions with the 2 and the 3. And it's so difficult, time-consuming, and everything for the boards to change anything. It takes them a long time. As far as we know, they're not updated to the 1.5 and 2.5. They're sticking with the old numbers and throwing in not accounting for heat. And it's correct. It's just kind of an old convention. So because they're sticking with the old numbers and throwing in not accounting for heat, I'm going to stick with the old numbers and throw in not accounting for heat. We're correct. It's just now we typically don't do that. But having a little bit of an older convention and passing the boards is a better deal than getting all hung up on half an ATP that's not going to change the course of your career as a chiropractor. So my 3 NADHs are going to give me 3 ATP each. My FADH2 is going to give me 2, not accounting for heat. My GTP gives me 1 for a total of 12 ATP for one round of the Krebs cycle. But I'm actually getting from the Krebs cycle the equivalent of 12 ATP. So the way we say it is kind of weird. It's like I've gotten checks for 12 ATP or a check for 12 ATP. And what we mean is, let's go to the check thing. If I have a check for $30, I'll say it's the equivalent of $30. I won't say it's $30 equivalents. It makes it sound like 30 things. I'll say it's the equivalent of $30. But in ATP, we'll say it's 12 ATP equivalents. It makes the check sound like 30 things, but what we mean is it's the equivalent of 12 ATP. So, in one round of the Krebs cycle, here's my products. No one argues. These are my products, plus my carbon dioxide, stuff like that. What that gives me is 0 ATP. How many ATP do I get? I get 0, big fat 0. Somebody might give you more information than you need for that, but you still get 0. How many ATP equivalents do I get? I get 12 equivalents per round. Here's one of the hard things with this. One of the hard things is when you get asked how many ATP equivalents, the question has to say how many equivalents. Easy, it's equivalents. When you get asked how many ATP, we tend to say in class how many ATP, real ones. No one's going to say real ones. They'll just say how many ATP. And especially if they give you more information than you need, it's, well, do you mean equivalence or do you mean the real thing? Unless you see that word equivalence in your face in the question, it doesn't mean equivalence. So that's a big, you've got to trust you on that kind of thing. So let's go back over here. For one molecule of glucose, I'm actually doing 2 Krebs cycles. So I've got that one glucose that gave me 2 pyruvate. Each pyruvate gave me an acetyl-CoA, so I'm actually doing 2 Krebs cycles. So let's go through and do some stuff here. So for each Krebs cycle, I made the equivalent of 12 ATP. So when I take the equivalents from those Krebs cycles and make ATP out of them, I'm going to get 24 ATP. So in the Krebs cycle, I got those 12 ATP equivalents times 2 rounds of the Krebs cycle, because we're going to do per glucose. That's going to actually give me, when I cash those checks, 24 ATP from converting those NADHs, those FADH2s, and those GTPs. But let's go back and look at something else. Remember, we made ATP in glycolysis. So we made 4, it cost us 2, and that left us 2. So I have 2 ATP from glycolysis. I also have those 2 NADHs that I made. So those 2 ATPs are going to go and give me 2 ATP. That arrow is pretty awful. Then those 2 NADHs are going to go and give me 6 more ATP when I cash my checks. When I did the pyruvate dehydrogenase complex, I also got an NADH for each pyruvate. So I have 2 NADHs. They're going to go and give me 6 more ATP. So when I actually add up everything I'm going to get from that one little glucose, once I cash all my checks, I'm going to get 38 ATP from that glucose, not accounting for heat. The term you're going to see for that is the complete oxidation. So the complete oxidation of one molecule of glucose gives me 38 ATP. So the term complete oxidation means take all the equivalents, convert them to the real thing. So 38 ATP, not accounting for heat. So my next question would be, if I were a student right now, well, what if you're accounting for heat? Here's your strategy. And this would be my strategy, at least with this class, might work with others. Most of the time, when you get multiple choice questions, when they're number questions, whoever's writing the question is careful not to make numbers too close. So, and I've tested this theory looking at a lot of different questions. Look for the answer you're looking for, the number you're looking for. If you don't find the number you're looking for, look for the next closest number going down. Most of the time, that strategy works because of the space people have to put in between the the options, because the close options don't work for particular reasons. So look for the next closest answer going down, and you should be good. Okay, so what we did here is we counted the equivalents in the process that we made them in. Let's do this a little bit differently. And I'm going to leave this diagram, and I'm just going to add a category and kind of write over numbers so you can see how you want to do it. So we have another process called the electron transport chain. That's where all the equivalents get converted to the real thing. So we make the stuff that makes ATP in the Krebs cycle, and we send everything to the electron transport chain. So what you might choose to do is count your equivalents there instead of in the process in which they were made. So this is that idea we had right at the beginning where we said, let's say I'm your accountant, or no, I'll be a new patient. You can be talking to your accountant, and you treated me today, and I'm an insurance patient, whatever. The cost of my visit was $150, but it's going to be a couple weeks before you get that money from my insurance company. Do you want to count that $150 today, date of service, or do you want to count it 2 weeks from now when it goes in your bank account? Very likely you're going to just tell the accountant, tell me what to do and I'll do it. So the way I just did it now would be like you're counting it on the day of service. You're counting the equivalents in the process in which you made them. You might decide instead to count them put them in the electron transport, count the money the day it went in your bank account. So these two NADH will go down here. So they're gone from here. We'll have 6 ATP here. These two NADH will come down here into electron transport. So we get 6 more. These 24 equivalents will come down here. So what we're going to end up with down here is the 36 ATP. This is gone and these are gone. And just that 2 here, still totaling 38. So in that slide in the glycolysis PowerPoint, where I said you're going to go back and do your numbers the way you want them, this is what I mean. I like it, and I did it in my office too, because I wanted to see when I was busy, when I wasn't. I like stuff where you made the equivalent. You might want to say, no, that's not usable, spendable ATP. Let me put it down here under electron transport where I actually get the real ATP. You might say, I don't want that $150 showing up on the date of service. I couldn't use it for anything then. Let me count it on the day it went in my bank account. That's when I can actually use it. Pure preference, but the important part is you knowing which way you did it so you could backtrack it. You're still going to get to the same number, but you need to know how you got there. Okay, so that's it for the Krebs cycle. You're going to have questions to do and a quiz and everything. Then we'll move on to the electron transport chain.